Yeah, maybe we can get started. Uh, Hey everyone, we are very happy to have Matthew Dodelson today. Uh, he's going to tell us about Ringdown at finite coupling. Yes, please go on.
Okay, well, thanks for the invitation and for the introduction. It's nice to be in India virtually, much easier than being there in person. So it's nice to have this opportunity. Um, I'm going to be talking about ring down behavior, and I'll tell you what that is. In particular, I'm interested in the SYK model. So here's a brief outline. So I'll start with the motivation. And then I'll tell you about quasinormal modes and how they encode the geometry of black holes. So that's a description purely from the gravity perspective. And after that, I'll move on to the boundary theory, and I'll tell you how to compute quasinormal modes in purely in perturbation theory. And as a byproduct, we'll see how the arrow of time emerges on the boundary. And lastly, I'll apply this formalism to the SYK model, and we'll see what the spectrum of quasi-normal modes looks like in the SYK model away from the holographic limit. And I'll conclude with some open problems. So we're interested in this thermal correlator. So I'll call it C of t, and it's the 2-point function of some operator O. O should be some local operator, or it can be in momentum space. But I suppressed that label here. So this is a function of time here. And to compute the thermal correlator, you compute this trace weighted by e to the minus beta h, where beta is the inverse Hamiltonian and h is the beta is the inverse temperature and h is the Hamiltonian. Now, I'm interested in a system with infinite entropy. So that means like it could either be a spin system at infinite volume. In that case, the entropy is obviously infinite. Or it could be a large N system, which has an infinite number of local degrees of freedom. And in both cases, we expect CFT to go to zero at late times, which is the statement of thermalization. But the question is, how precisely does it go to zero? Is it a power law decay? Is it an exponential decay? Is it something worse? So we're trying to characterize the different options. And one really simple possibility is it's just a sum of exponentials. And we want it to go to zero, so the imaginary part of the omega n should be less than zero. And the dn's are just some complex coefficient. So if you're familiar with black hole mergers, when two black holes merge, there's this final phase of the process that's called the ring-down phase. And in that phase, the signal looks like this. And the omega n's are just the quasi-normal modes of the final black hole. So I'll call this behavior ring-down behavior. I now want to Fourier transform CFT. So I go to frequency space, and in this description, these complex frequencies omega n become discrete poles of C of omega in the lower half plane. So I mentioned this vague connection to black holes, but of course this is made precise in the ADS CFT correspondence. So in this situation, we have an infinite n gauge theory, and if we work at infinite coupling, we can do the computation in an ADS black hole. And in this situation, the poles of this function C of omega are just the quasi-normal modes of this ADS black hole. So in particular, what I drew here was n equals 4 superheating mills, add strong coupling. And we could compute the 2-point function of scalar glue ball operators, trace f squared. And then it forms this tree structure. And they go off at a finite angle into the complex plane. And what I drew here was ADS5. But in other dimensions, it looks qualitatively similar. The asymptotic angle just changes. And also, I want to say that the lowest modes here are not exactly on this straight line, but you can compute them numerically. And at large mode numbers, they approach a straight line. So this is sometimes called the Christmas tree of quasi-normal modes. So that's a strong coupling. Now let's think about free field theory. So this is the only other case where we can do the computation. And here it's even simpler because we just have free large N fields. And here we get a very different picture. So here we get, instead of discrete poles, we get cuts. And the cuts extend from minus k to plus k, where k is the spatial momentum that labels these operators. And we have these cuts in the complex plane. So these two pictures look very different. And there's a
Sorry,
basic,
Matthew, in the previous slide, we were only considering k equal to 0, or this Christmas tree is there even for finite k?
it's there for finite k. The lower modes are affected, and they have, yeah, the lower modes have an interesting structure at large k, but this asymptotic Christmas tree is always there.
So you fix k and you go to this asymptotic limit, it will always be this line.
Yeah, absolutely.
Okay, and of course, I mean, you will never see cuts in a tree level GR computation, right? Just solving some wave equation.
Absolutely. Yeah. So these two pictures are very different. So strong coupling and free field theory are, I mean, there's no contradiction. They can be different, but we can still ask the question, what happens at finite lambda? You might think that at lambda equals 1/100, these cuts decondense into a series of discrete poles. Or you might imagine that there's some phase transition at finite lambda, and we just don't know the answer. So
La
this,
Lambda is the 't Hooft coupling.
yes.
Okay. And I don't know, maybe this is a very silly answer, but a question, but where do these cuts come from? I mean, because I mean, what are we looking at? If you were looking at a massive particle, you would look at the poles of the propagator. Where are the
Yeah.
cuts coming from?
Yeah, it comes from the fact that it's a Yang-Mills theory. This computation was done by Hartnell and Kumar.
Okay.
Yeah. So it's some phenomenon. I think it's called Landau damping. These cuts are called Landau damping. I don't know the physics of them. Yeah. But usually in free systems, you see cuts. Yeah.
But one point is that this is like a 2-point function of some operator like phi square. So it's a bilinear in the fundamental field. So the leading diagram is actually a one loop diagram.
Mm.
So that is where the cut basically is coming from. So it's like 2-point function of phi square, phi square.
I see. I see. I see.
So basic QFT. Okay, thanks.
Yeah. Thanks, Fargo. Right. So yeah, I want to understand what happens at finite lambda. Of course, I can't actually do this computation. Now there are various analyses of this. So you could imagine trying to do a resummation of perturbation theory at weak coupling, and people tried that, and I think the story is not complete, and they find poles and cuts. So that's what you usually get in that analysis. You can also try to do some naive holographic extrapolation where you perturbatively correct the metric, and you can never get cuts that way. You can only get poles. So I think both of these strategies, they might be good toy models, but one really needs to solve the problem exactly to find a convincing answer. So another way to ask this question, at finite lambda, we have some very non-local stringy black hole. And you could ask, what does this stringy black hole look like? What happens when you hit it with a perturbation? And this is a hard question, of course, to answer at the level of the metric or the space-time fields. But we can instead ask about the QNMs. And this ring down behavior might be able to tell us something about the stringy geometry. So that's the philosophy I'll take. So what we'll do is we'll identify features of the quasi-normal mode spectrum that tell us about geometry, and then we'll see which ones survive at finite coupling away from the holographic limit. Any questions about this motivation? Okay, so now let's review quasi-normal modes, and we can see how they encode the geometry of a black hole. So we're at lambda equals infinity, and we need to solve this classical wave equation on the background of the black hole. So in particular, we're above the Hawking-Page transition, where holography instructs us to do the computation on an ADS black hole. And here I just wrote down a general spherically symmetric black hole, static also. And it doesn't really matter what f of r is. This discussion is going to be general. So the wave equation is given in the second line. So we Fourier transform to frequency space. And then we have a wave equation for this variable psi. This is a massive scalar. And it looks like the Schrodinger equation for a particle in a potential. So here, z is called the tortoise coordinate, and it's defined by dz equals dr over f of r. So it's just a convenient choice of coordinates for this problem. So there are various Green's functions we could compute on the boundary, retarded, Whiteman, etc. The easiest probably is the retarded Green's function. And to compute this quantity, you look for a mode which is purely ingoing at the black hole horizon, which is at z equals infinity. And then you read off the behavior at z equals 0, which is the ADS boundary. And there's a non-normalizable behavior, which is the coefficient of delta minus here. And then there's a normalizable behavior, which is given by the coefficient of z to the delta plus. And the retarded Green's function is given by the response over the source. Now, we see that when this source A equals 0, the retarded Green's function blows up. It has a pole. But also when A equals 0, the source vanishes. So the mode is purely normalizable and ingoing. And that's what we call like a quasi-normal mode, a normalizable and ingoing solution. So the lesson is whenever you have a pole of the retarded Green's function, you have a quasi-normal mode. So I want to do a few examples, and the lesson I'm trying to draw from these examples is that you can see geometry in the spectrum of quasi-normal modes. So here's my first example, and this is a black brane in ADS. So f of r is r squared minus 1 over r squared. In the case of a black brane, this is dual to a field theory at infinite volume, and because it's a CFT, you can rescale the temperature. And so there's no dimensionless invariant quantity here, and so the metric just has a 1 in it. Yeah, there's no beta. That's a physical quantity. And here the potential is monotonically increasing. And so we start at the singularity where it's minus infinity, and then it vanishes at the horizon. And then as you go to r goes to plus infinity, it diverges, the potential goes to plus infinity. And the solution can be computed for the quasi-normal modes. and you find this Christmas tree. If you want to analytically find this Christmas tree, you can use the WKB approximation for the wave equation. So I want to point out that, we have these two lines of poles, and these should be thought of as anti-Stokes lines for solutions to the wave equation, over which the asymptotic behavior changes dramatically. And so we have two asymptotic regions of the complex plane that are separated by these lines of poles. The first is the ordinary high energy limit. Omega goes to plus or minus infinity. And then this is, of course, a natural limit to take. You just hit the system at high energies, and you might want to do that. And in fact, this probes the operator product expansion in the CFD. The other limit is very weird, and it only exists because the function is analytic. But if you were somehow able to compute the function infinitely precisely on the real axis, you can analytically continue to the lower half plane, and then you could go to this limit omega goes to minus I infinity. So this is not a natural thing to do, but in the black hole background, it has a physical meaning, which I'll now discuss. So what is this limit? Suppose that we were to do the WKB approximation and to look for turning points.
Sorry, Matthew, can I ask on the previous slide? So this, even restricting to real omega, the behavior at omega being plus infinity and minus infinity can be different, right?
So the KMS equation relates them.
Right. So in principle, you can think of this extra exponential that comes in the KMS relation as some kind of Stokes pole that you have picked up in changing the argument from 0 to pi, right?
Yeah. So it's a little more natural to work with a two-sided correlator, in which case you don't get an extra exponential. But
and why did you say that this omega goes to minus I infinity is unnatural? I mean, typically I could do it even for a non-holographic system, right? I could look at this limit.
I think it assumes meromorphy. Like if you didn't have a meromorphic extension of your correlator to the full lower half plane, you just wouldn't be able to go down there.
But typically we have it, right? I mean, even for a general system, the retarded Green's function has a extension, no?
No, I don't think so.
Why do you say that?
It's analytic in the upper half plane, right?
Yeah, but then typically, even for a hydrodynamic system, there are these sound pole and diffusion pole that are there in the lower half plane, and so there is some meromorphy in the lower half plane.
I certainly agree that those low hydro modes are there, but even in hydro, you have cuts because of the hydro EFT. So in general, there's a cut that comes from the origin. So that's a general quantity, and then as you go out of the hydro limit, we just don't know anything. It could be that you can extend to some point, and then it just becomes a mess. Yeah.
Okay.
Yeah, and in the SYK example I'm going to give, this limit is much more subtle, and going to minus is not something that you can maybe do. Yeah. Okay, so let's try to understand what this singularity means, what this limit means physically. And if we were to do the WKB approximation, you would look for turning points of this equation. And imagine that we want to get very high energies in this turning point equation. So if we look at the potential, the first way we could get high energies is to go to R goes to plus infinity, which probes the ADS boundary. And in this limit, V goes to plus infinity. And so omega goes to plus or minus infinity. So this natural high energy limit is probing the boundary of ADS. The other way we could get large energies is to go to R equals 0, which is the black hole singularity. And in this context, VOR goes to minus infinity. And so therefore, omega goes to minus I infinity. And this is actually probing the black hole singularity. So this new limit is a signature of the black hole singularity. And here we see a few geodesics. And geodesic 2 is bouncing off the black hole singularity. And that's what's being captured as you take omega goes to minus I infinity. So this is called the bounce geodesic because it's a null geodesic that bounces off the black hole singularity. And I just wanted you to remember for later that if we consider the Whiteman function, the behavior of this Whiteman function, if you use the WKB approximation, is that it exponentially decays with frequency at omega goes to minus I infinity. So this is one signature of the black hole singularity, this exponential decay in the lower half plane. This is not there, for instance, in the BTZ black hole, which has no singularity. Okay. So let's give another example. So now I want to add a charge to the black hole. And so I modify the redshift factor by q squared over r to the fourth. And so now it's unchanged at large r, but at small r, the potential instead goes to plus infinity. And we have this stable minimum here where the potential is negative. So the new feature in the quasi-normal modes, so we have our standard Christmas tree, and then we have modes along the imaginary axis. And these are virtual bound states behind the horizon that are localized at this stable minimum.
So there's only a finite number of these purely imaginary guys.
There's actually infinitely many.
Okay.
Yeah. They can fill up this potential all the way, basically.
But typically, I would have thought if you have a 1D potential with a finite depth, the number of negative energy states here would be finite, right?
Yeah, I think it's not quite negative energy.
Well, V of R was yours, you were setting it to omega square, right?
Yeah, but oh wait. V of R equals, yeah, good. Yeah, you would think that that's correct. Yeah, I don't immediately see why, but I think if you do it numerically, you get infinite.
Okay, you're just saying there are actually infinite number of them, and that's.
I think so. Yeah,
Okay.
but I agree that's confusing. Yeah. Right. So I wanted to point out that there's now two new asymptotic regions. So they're now complex, and you can go on either side of this imaginary line of poles. And again, you get exponential decay that's now probing the time-like singularity of the black hole. So here's my third example. And this is, instead of a black brane, we now have a finite volume. And here's the metric. So we now have a physical scale, which is the temperature, which is related to mu here. And if you take large angular momentum, the potential now has a metastable minimum and an unstable maximum. And this unstable maximum is called the photon sphere. So at large angular momentum, you have the structure of quasi-normal modes on the right-hand side, and they're almost real. So what this means is that they're localized at this metastable minimum that's very far away from the black hole. And in order to decay into the horizon, they need to tunnel over the barrier. And so that's why they're almost real. If instead you want to probe not this metastable minimum, but the unstable maximum, It turns out what you can do is to take the angular momentum to I infinity. So that's a limit you can take because everything is meromorphic in spin. And what you find is this iconal spectrum of quasinormal modes that you might recognize from asymptotically flat black holes. And capital omega is the velocity of null geodesics at the photon sphere, and gamma is called the Lyapunov exponent, and it measures the instability of the photon sphere. And so these are intrinsic geometric quantities that characterize the photon sphere, and you can compute them by taking the limit L goes to I infinity.
So in deriving this formula, you're taking L to I infinity, but this omega L that you wrote, is it true for real L as well?
No.
No.
So for real L, you get the picture on the right-hand side,
Okay.
which is not this. Yeah. So there's something funny as you vary L.
Wait, so why did you say it's like flat space? Because in flat space, this L would be real, right?
Yeah, so in flat space, you could go in any direction you want in the complex L plane, and you always find this spectrum. In ADS, you have to take L goes to I infinity, and then you can take the flat space limit if you want, and you recover the right answer. Right.
So these omega n's are purely imaginary if L is purely imaginary.
Absolutely, they're bound states. Okay, so the lesson that I tried to get across in these three examples was that you don't really need to look at the metric if you want to study geometry. You can look at quasi-normal modes, and that's at any rate a more natural quantity from the point of view of the CFT, because you just look at the 2-point function. You don't have to do some HKLL reconstruction of the metric or some complicated thing. You just need to look at the 2-point function, and you can read off the spectrum. So you can learn about geometry from the 2-point function of in a CFT. Okay, I want to move to the boundary now. Are there any questions about that discussion?
I'm sorry, just about your last comment. I mean, to really make that statement powerful, one would have to argue that even for a generic singularity, you get these behaviors, right? I mean, here we are doing calculations in some special, very symmetric kind of black hole. So it's not really fair to say that you are probing a generic singularity or something, right?
Yeah, so I agree. You can play around with things, and there's a Mathematica package that lets you compute the quasi-normals of any black hole, not even obeying Einstein's equations. And if you take a metric that has a black hole singularity, you always find a Christmas tree. I don't have a theorem, but it's a numerical experiment you can do. So you always have asymptotic poles going off at some angle. Okay, so we're halfway through, and now we can move to the boundary. So I now want to compute these things, and I'm going to make a few simplifying assumptions. The first being that the temperature is infinite, and this simplifies things because now we just need to compute trace O of T of 0. The second assumption is I don't want to do quantum field theory because in that situation you have a singularity when the two operators hit each other. If I just assume quantum mechanics, then I don't have that singularity, and C of T is non-singular at T equals 0. And finally, I want to specify one-dimensional coupling J, and it has units of energy. So these are three pretty simplifying assumptions. But under these assumptions, I can now Taylor expand CFT because it's non-singular at the origin, and CFT is even. by definition. And so we get what's called the moment expansion. The mu n's are called the moments. And these completely characterize the correlator. Now, by dimensional analysis, because J is the only dimensional parameter, the mu 2n's have to scale like J to the 2n. And so the moment expansion is nothing but the ordinary perturbative expansion in J. It turns out that this has a finite radius of convergence, which I'll call beta naught over 2. In a general theory, this converges up to a certain radius. And the radius scales like 1 over J, again by dimensional analysis. In fact, you can make a stronger statement, which is called the universal operator growth hypothesis. And this is a hypothesis about the behavior of the mu's in chaotic systems. And so they have to have this asymptotic behavior as n goes to infinity. So that's something you can check in various examples, and it's believed to be true in any chaotic theory. So this is all to say that this moment expansion is very highly constrained by chaos and by this finite radius of convergence.
Sorry, who made this hypothesis about n to the 2n? Where is this?
Yeah, so it's equivalent to exponential decay of the spectral density at large real frequency, and it's a paper by Altman and Parker. It's the group at Berkeley.
Okay.
Yeah, the paper is called a universal operator growth hypothesis, so it should be relatively easy to find.
Mm-hmm.
Okay, and we have this moment expansion, and our job is to fit this expansion to these exponentially decaying terms. Now the left-hand side has a finite radius of convergence, but the right-hand side converges for all times greater than 0. So if we're able to solve this fitting problem, then we can actually determine the full long time behavior of the correlator. And we can use dimensional analysis to say that these omega n's are proportional to J. And so a solution of this fitting problem is actually a non-perturbative resummation of the perturbative expansion. Okay, so that's what we have ahead of us. So to solve this fitting problem, there's a general method which I'll now explain. So the idea is to truncate to a finite number s of exponentials. So we have our equation, and we truncate it at s exponentials, and then we solve the fitting equations on a grid of size 2s. So I wrote that here. So J goes from 0 to 2s minus 1, and we have discrete time steps delta t. So we have 2s unknowns, which are these dn's and these omega n's, and we have 2s equations. And so that's enough to solve for these quantities. And at the end, we're going to take s goes to infinity, and we're going to hope for convergence. So if our initial assumption was correct, that this is a discrete sum of exponentials, then this procedure is going to give the correct answer. So here I just drew the picture. So we have t and we have c of t, and we know the function over this short range over which it's not exponentially decaying, and we just fit to exponentials on a pretty fine grid. Okay, so how do you solve these equations? It turns out you can reduce them to linear algebra. So I'm going to introduce a little bit of notation. I have a Hilbert space of operators O, and the inner product is defined by trace O prime. So now we have operators, super operators that are acting on this Hilbert space of operators. And we want to find a super operator U tilde, and it satisfies this relation here. So if you evolve O by the jth power of U tilde, and then take the overlap with O, you should find the correlator at time j times delta t. So if we look at this equation I just mentioned, and we compare the left-hand side to the right-hand side, we see that the eigenvalues of U tilde are just each of the minus I omega n times delta t. And so this is an operator whose eigenvalues are the quasinormal modes. So now we want to solve for this operator, because if we can find an equation for U tilde, then we can compute its eigenvalues. And so we make an ansatz where the eigenstates are just a linear combination of U tilde to the j acting on O, and this plugging this in leads to a generalized eigenvalue equation for these coefficients, where these matrices Mi, Mk are defined in terms of the correlation function on the grid. And so now we have an equation that we can put on a computer, and we can solve for these omega n's and these dn's.
Sorry. So is this Hilbert space of dimension capital S? Like, why are you taking this omega n to be a linear combination of S terms? I thought S was something you introduced to truncate the exponentials.
Yeah, so if we look at this equation for U tilde for the matrix elements of U tilde to the j,
Yeah.
it has S eigenvalues, which are these omega n's. So the Hilbert space has infinite dimension, but U tilde can be taken to be a finite dimensional operator.
Okay. And what are the matrix elements of U tilde j between two non-identical states, between O and O prime?
Yeah, so once, you can solve for that. I mean, if you rewrite O prime as a linear combination of U tilde to the j O's, then you can use this relation to solve for them. So,
but I mean, typically the quasi-normal mode frequencies will depend on which operator you're starting with, right?
Absolutely, yeah. So we're implicitly reconstructing a U tilde for each operator.
Right. So that's what I'm asking. So if U tilde kind of depends on O, then how do you define the off-diagonal matrix elements of U tilde j between O and O prime?
So if O prime is a linear combination of U tilde to the j acting on O, then you can do it using the relation I wrote here, right? Because we know any power of U tilde to the j.
Okay, but what if the operator is not like that? What if it is not?
Yeah, so we don't really need to know that, because we're finding I don't think this operator is unique, but we're finding a certain operator that solves this problem, and we're defining it by its matrix elements in that subspace.
So you're saying you have this capital S dimensional subspace, which is O, U tilde O up to U tilde to the S minus 1 O. And that's the space you are restricting to.
Yes, absolutely. If you want, you can just project onto that subspace and solve the problem that way. But I think one way to say it is that we're only computing the quasinormal modes for this operator O. So we would have a different U tilde for every O.
Right.
Okay. So it might be helpful to give a couple examples. So here I have two functions, and they both have radius of convergence 1. And the first one is 1/Cauchy, and that thing exponentially decays at late time, and it has ring-down behavior. And the second example is C of t is 1/t² + 1. This thing is parallel behaved at late times. Now, what I plotted on the left-hand side is the Taylor expansion truncated at some large order. And we see that the functions look pretty similar. It would be hard to tell that one was exponentially decaying and one was parallel decaying. But in the first case, this procedure gives a discrete spectrum of modes, which is the correct answer. And in the second case, we get a large number of eigenvalues that are condensing on the imaginary axis. So this is a branch cut, which is expected whenever you have parallel decay. So this procedure allows you to extend the function to arbitrarily late times if it's exponentially decaying. And in that case, it converges to a discrete spectrum of eigenvalues. So I want to say a few words about what just happened. So we started with our function C of t, and then we fitted to sum of exponentials by making an operator U tilde whose eigenvalue are the quasinormal modes. So these are, of course, complex, and so we've been able to construct a non-unitary operator U tilde, which acts as a time evolution operator. So we have, in some sense, non-unitary time evolution, and so the arrow of time has emerged. Now we started with this very strong assumption that we have a discrete spectrum of omega n's. If this assumption is okay, then the spectrum is going to converge in the limit of s goes to infinity. If not, then we have accumulation into cuts. So as you can see in the lower picture here. So we have an assumption, and now we can check that assumption by doing this procedure. In the context of classical chaos, you can also construct U tilde in a more physical way by course grading the time evolution operator or smearing it. And in this classical context, these are called Rouel resonances. And if you make some strong assumptions about how chaotic the system is, then you get a discrete spectrum. Also, in holographic theories, U tilde should be an operator whose eigenvalues are the QNMs. And this was recently discussed in the context of the double cone geometry by Chen, Ba, Aldacena. And in this context, you can get a non-unitary operator by introducing an I epsilon prescription at the black hole horizon, which is necessary for regulating the double cone geometry.
Question.
Yes.
If I can ask. So I mean, all of this is in the framework of ADS-CFT, right? When you're
Yes.
talking about constructing a operator and so on and so forth. So in ADS-CFT, we already have a time direction, right?
Yeah.
So in what sense is this, and different from that?
Yeah, so we have a time direction that generates unitary time evolution, but what they discussed in the context of holography is how do you find a time evolution operator which is non-unitary, whose eigenvalues are dissipative, and so that's more of an error of time. So and so they construct this modified time evolution operator U tilde, and this thing is dissipative instead of being unitary.
Okay, I mean, I don't want to stress the point too much, but yeah. Okay.
So but I mean, just one point. I mean, this U tilde for a general system. I mean, you're fitting some small time expansion to a late time expansion, right? Like your power series is some early time expansion, and that has some finite radius of convergence. But strictly speaking, the sum of exponentials should only be true at late time. So rigorously speaking, have we defined this operator U tilde or?
Sorry, the sum of our exponentials is convergent for all times.
But I mean, are you saying that that function is exactly equal to that sum of exponentials?
Yes. I mean, at very early times, it's not going to be dominated by the first exponential, but you can still write a convergent sum. So that's kind of the power of this assumption that you have this moment expansion, but then you can extend to late times by matching at short times.
But then probably for a general system, this assumption that you can write it as a sum of exponentials probably won't be true, right? I mean, something has to be.
No, I think I think if it's chaotic enough, it's going to be true. So it's pretty powerful. But I agree that if it's for a completely general system, you're absolutely right. You have cuts. But if you get really lucky and the system is very chaotic, I think you're in business. Yeah.
Okay.
I don't have a proof, but we'll do one example where it works. Yeah. I only have one example.
Okay.
Any other questions before we do it?
Yeah, I mean, I just want to try to clarify this a little bit better, the arrow of time issue. So if you have a, ADS short shell black hole in equilibrium, right, then there's no arrow of time, right? I mean, it's symmetric.
There is a symmetric time evolution operator. There's also a non-symmetric time evolution operator.
Yeah,
takes...
of course. Yeah, no, and I know that. So my point is that if you just consider a black hole at equilibrium, it doesn't have any ring down, right? It doesn't have it's not in a state which corresponds to a ring down state. It's in a completely relaxed state, right?
But
let's say all the.
I think if you perturb it, then it's going to ring down.
Yeah, of course. So my point is that this arrow of time that you are saying is an emergent arrow of time in some way, right? Is that the correct way to phrase it? So my point is that it's too strong a claim to make that it's an arrow of time, because you're perturbing a system, then you're looking at the response of that system to that perturbation, and then you're saying that the response somehow.
But that's always how an arrow of time is, right? Like even in not a black hole, just any system which is in equilibrium doesn't have a time. To talk about decay, you have to perturb the system first, right? So that's not special to a black hole or something. That's also true for a gas in a box.
Sure. But in a gas in a box, we would not say that we have an emergent arrow of time because of that.
You do, right? If you start it in non-equilibrium state, it will equilibrate.
Yeah, sure. Okay. Anyways, I guess this is more of an abstract discussion, so I don't want to push it.
I agree with everything that everyone has said in the past minute. So I think we're all on the same page. Yeah. Okay, so let's do it. Yeah, I have to apologize. I know everyone works on double scaled SYK now, so I shouldn't really use Q, but I'm going to use it. So this is the Hamiltonian for SYK, and it has some random coupling J, and there's n fermions. We take n goes to infinity, and we have a Q pairwise interaction between them. So at the end, we should average over J, and the average over J squared defines our dimensionful coupling, capital J, and you should take this to scale in a certain way with n. So the nice thing about SYK, of course, is that at infinite n, we have this Schwinger-Dyson equation. And this is an equation for the exact propagator, and it's just a self-consistency relation that can be put on a computer in equation form, and you can solve it perturbatively in the coupling.
So you're just taking the 2-point function of the fundamental fermion, this psi.
Yeah. And the algorithm for computing perturbation theory to order n is polynomial in n. And so you can compute the moments in polynomial time, and you just put your computer aside and you wait for as long as you have to wait. And for me, that was 2 months. And so this gives 2,000 moments. And in terms of the numerical precision that you can compute the operator to, you have 10 to the minus 1200 digits of precision. And we need it because we're asking very subtle questions. We're going very deep into the complex plane. And so the more precision, the better. I should also say that this polynomial time algorithm to compute the moments is completely non-standard. So in a spin system, there are only exponential time algorithms, and the most anyone has done so far is 50 moments. So this is, you can do much better in SYK. And here's the answer. So let me explain a few things. So the color of these points is labeling the argument of this coefficient function dn. The size of the points is labeling the magnitude of dn, and this is on an exponential scale. So these dn's fall off very, very fast, and I'm plotting the size on an exponential scale. So there are some hollow points here, and those have not converged yet. The rest have converged to within a precision of a couple digits. So there are a few properties I want to point out.
Sorry, and just the location of the point is the corresponding omega n.
Yeah, that's right. So there are a few properties that we see. The first is meromorphy. We have a discrete spectrum with no cuts that can be seen numerically. Now, you might ask what I mean by that. So what I mean is up until around here, which is the imaginary part of omega is of order 5, all the poles have converged to 4 digits. And I see no accumulation points. The first pole has converged to 40 digits. And I see no sign of a branch cut.
So
This
you're
is
doing infinite temperature here, or?
Yeah.
Infinite temperature. And then, so J is the only scale.
Yeah, so I said J equals 1 here. And yeah, of course, you can never prove meromorphy numerically. You need to maybe have some theorem. But
if I may, what is the n here? Like
n,
you have taken n to infinity, or what is
the? Yeah, so I need infinite n in order to get a continuous.
So the numerical simulation is for solves the large and Schwinger-Dyson equations.
Yes.
Infinite.
Yes.
Okay. And can you just clarify again this question about beta and j and so on? You said j equal to 1, and what is the beta?
It's equal to 0. So in other words, I have a very non-holographic theory. It's much simpler to take beta equals 0, and it's some very highly stringy black hole in the bulk.
So infinite temperature, J unity, infinite.
Yeah.
Is that okay?
Yeah. So, right. So I don't see any branch cuts. You would need to prove this, you would need some analytic argument, which I don't have, but numerically I see no cut. And then also, I would expect if you push this further, this whole spectrum is filled out inside this tree structure.
Sorry, Matthew, can I ask, your lowest quasi-normal mode is of order j, right? So the decay time is of order j, that j was of order 1. Now, does just the one loop term, let's say you just take the first diagram, the first correction, the first melon diagram,
Uh-huh.
does that have an imaginary part or not?
An imaginary part in frequency space?
Yeah, because typically how you get a lifetime, perturbatively is that you get a 1 over the propagator, and then the self energy gets an imaginary part.
Yeah. Yeah.
My question is whether the lowest quasi-normal mode can be seen just from that lifetime or
I
not.
think definitely not.
No, okay.
Um,
Or you think you need this whole resummation to get that thing?
I don't remember exactly what it looks like, but yeah, I think that would fail. I can take a look again.
But do you know if this two loop diagram has an imaginary part or not, or what is the?
I don't know. Yeah.
Okay, okay, fine. That's
I expect it wouldn't work. Yeah, so I expect if you push this further, you fill out the full Christmas tree. So the other thing I wanted to say is that
Can I ask again? So how many points are there? I mean, in this?
well, it depends if you count reflections along the y-axis, but let's say 30, 40, something like that.
Yeah, so you have like a first 40 quasinormal modes with yeah, with counting the degeneracies also. Okay.
So the second thing is that we have a tree structure. So what I mean precisely is that the edge of the spectrum is two straight lines at an angle from the real axis, which is what we found in holography also. And the final procedure, and then the final property, I asked you to remember that in the holographic theory, the signature of the black hole singularity was exponential decay of the Whiteman function. And something that's equivalent is exponential decay of the residues, dn. And you can check that here also. And you find precisely exponential decay of the residues. So this is all to say that if you probe a stringy black hole, it looks a lot like an ordinary black hole with a curvature singularity. Now, the main difference is that the spectrum inside the Christmas tree is also filled in this case. And so you might want to ask what happens to the black hole singularity at finite coupling lambda. So that's a question that we all want to know. And I don't know how to address this question, but you might want to look at the behavior of the spectrum at omega equals minus I infinity. So that's way down into the complex plane where my computations have not yet seen the spectrum. And you might guess that this is some kind of random matrix theory behavior. So that's just a guess. But we see that on the edges, it looks very straight. And then inside it might be more random. And so that's one guess for what you get if you were to push down further. Okay, I'm running out of time, so let me move on. You can take the large Q limit of these results, and what happens is the tree closes in. So this is Q equals 6, and the angle slowly comes in, and then by Q equals 20, they're all imaginary.
Question?
Yeah.
No, so we're talking about a correspondence between this and the spectrum of charge and rotating black holes, right?
You mean
So-
these higher black holes, or?
No, I mean, you described the spectrum for charged and rotating black holes, and they have certain characteristic shapes, right? And now you're talking about the SYK model. So in the SYK model, where is the angular momentum and the charge? Like what are those
Right. So let me
in
correct.
the S? Yeah.
Yeah, I wasn't particularly clear before. So so what I meant was by the angular momentum, that was the angular momentum of the perturbation, not of the black hole itself.
Oh, right. Okay.
So here, I don't have anything like the charge or the angular momentum because, well, this is a 0 plus one-dimensional field theory, and there's no angular momentum. The charge, you might think that the higher dimensional extreme black hole might have a charge, but I don't have any real black hole description. The only thing that looks like a black hole is this Christmas tree and the exponential decay and the meromorphy. But it would be interesting to find a model where you could see some of these other features of a black hole. Yeah. There's a question on chat. When the modes become purely imaginary, do you recover the spectrum for black holes in JT gravity? And let's wait for the next slide. Now, at large Q, the QNMs all become imaginary. And the reason is because at large Q, even away from low temperatures, there's this emergent ADS2 dual that was pointed out by Lin and Stanford. It's called the fake disk. But it's just an observation that the spectrum at large Q is equal to the spectrum of quasinormal modes of an ADS2 black hole, which is just ADS2 in different coordinates. So you can model the transition from large Q to Q equals 4 by adding terms that are singular at R equals 0. And it doesn't really matter what you add. You just increase these LIs, and you find that the modes leave the imaginary axis. So this is a crude model where we just take an ADS2 geometry, we add something that's singular at the black hole geometry, compute the quasinormal modes, and you find a Christmas tree. And so that was just meant to be a model for this transition. Okay, that's it. Let me give some open questions, unless there are questions about this. All right, so just a few questions. You might think that this meromorphy property is a general property of large N chaotic systems, but there's a counterexample, which is mass deformed SYK. So this model is integrable at low energies, and if you repeat the same process, you find branch cuts in the correlator. And the question is, what is the physical interpretation? And what are the lessons for higher dimensional gauge theories? Also, you might want to see a photon sphere, in particular these iconal modes that I discussed before. And you might want to look at higher dimensional versions of SYK and solve the Schwinger-Dyson equations in that context. And finally, of course, one wants to look at more realistic systems. In the 3D Ising model, it's not known what's the lowest QNM, and in QCD, it's going to be more difficult, but it's also not known. So these are nice goals for the future. Okay, thank you for having me.
Okay, are there any questions?
Yeah, maybe I can ask the question. So you said you calculated these moments, right? These coefficients of t to the 2n. Do you have a plot of them or something? How does it look like?
You want the muse?
Yeah, the moments themselves.
Yeah, I can go to Mathematica. I have to apologize in advance for this horrible notebook, but there is a plot there. Here they are. So they're going to be very regular. So this is the log of the muse, and it grows more or less linearly. Yeah. But it's not like there's some structure. Yeah.
So these muse are all real?
Yeah, they're all real, and they're all positive. In fact, they're all integers at infinite temperature.
So somehow the dn's and the omega n's you get sort of add up in pairs to get something real. Like that's why there is this left-right symmetry in your
yes.
thing. Okay. Okay, and you compute these in real time, right? Not in, okay.
Yeah, I mean, the thing is that these are inherently Euclidean things because they're just thermal one point functions of nested commutators of the Hamiltonian, because you take n time derivatives and you pull down commutators of the Hamiltonian, and so these can be computed purely in Euclidean theories.
Yeah. So I have one more question, but maybe I'll wait if other people want to ask something.
Maybe I can ask a naive question. Instead of finite Q examples or large Q SYK, you briefly mentioned DSSYK. Could you repeat these numerics for the double scaled SYK?
Problem is I haven't read those papers, so I can't answer your question very well. But I know that people have certain expressions. I don't know if you can read off these moments in when p squared over n is fixed. I'm just not sure. But it would be interesting to see if these poles turn it into cuts.
Yeah.
So that's one guess maybe. Because it's become more quantum.
Yeah, maybe Raghu, if you have
Yeah.
another question.
Yeah, I
you can
was
go
going to
ahead.
ask, maybe also you haven't read those papers, so feel free to not answer this. But this thing of repeatedly applying the Hamiltonian seems a little bit like these discussions of Krylov complexity that people have been talking about. So
Well, those
is this, sorry?
papers I have read, yeah.
So is this data that you're generating about the moments tell you something about that, or what's the relation with this Krylov?
Yeah, good. So the Krylov complexity is just this beta knot that appears here. This is the coefficient of the linear growth in the Krylov complexity. Yeah.
Mm-hmm.
So it's equivalent to knowing the location of the first imaginary pole on the time axis. Yeah.
You mean where the radius of convergence, what the radius of convergence is?
It's also equivalent to knowing the exponential decay rate at real frequency.
And just sorry, one more thing about this Ising model. So what's the idea? You would want to calculate the 2-point function of the sigma operator or the epsilon operator?
I think you need sigma. So you want to get rid of hydro cups, and so
Okay.
you want to choose something which is D2 odd, and so it doesn't couple to the stress tensor, and the conjecture would be sigma is meromorphic. So you can imagine computing the first 50 moments on a computer, and working directly at infinite volume, and on the spin system, and then you could go to the quantum critical point and see if you can extract the exponential decay.
But you will set it at just in real time, the operators would be separated just in time.
Yeah. It's best to go to frequent or spatial momentum space, because then we expect.
And you will somehow generate these moments. So you will work with the quantumizing model, the Hamiltonian version of the thing.
On a lattice, yeah.
On a lattice. So 2D spatial lattice and
Yeah.
I see.
And then for QCD, you can imagine doing a lattice gauge theory computation. I don't know if it's feasible. There's a question.
So I have may I go ahead?
Yeah.
So in one of the slides, you made a statement that the behavior of the QNMs of the stringy black holes are similar to the normal black holes.
Yeah.
So So by that I mean that you mean normal like ADS black holes in GR.
Yeah.
Yeah. So basically here, like since you don't have the black hole solutions, stringy black hole solutions, that is why you are computing the QNMs in the field theory side, right?
Yeah.
So recently there has been some discussion in the literature about instabilities in the QNM spectrum. That is, the overtones of the quasi-normal modes are unstable, and those notions. So, like, are you aware?
Unstable as a function of the parameters in the theory?
Yeah. So suppose like you suppose you change the underlying potential by an amount epsilon. The
Yeah.
change in the spectrum is of an order much better than epsilon. So, yeah, so these notions have been sort of formalized using this idea of the pseudo spectrum. I was just wondering if those QNM instabilities can be probed in the framework that you are using. Like, can we?
So I think it would be very interesting. So let me make a comment on the boundary side. So on the boundary side, if we have some chaotic system, we could define these real resonances, which are the QNMs. And there's a theorem that unless the system is what's called structurally stable, which is a certain topological notion, if it's not structurally stable, then these resonances are unstable functions of all parameters in the Hamiltonian. So that's the boundary dual of what you just said. Now, I think it's true that the QNMs in gravity, they're not unstable to arbitrary perturbations. They're unstable to random perturbations. Is that fair to say?
Actually, if I recall correctly, that you can also, in addition to random perturbations, I think you can sort of make deterministic modifications, like modify the potential by adding a cosine term, and still show that some of the overtones are unstable.
Yeah. So all I meant to say is there are some perturbations for which they are stable, right?
Yeah.
Like you can imagine just increasing the mass of the black hole, and then they're certainly stable. So I think for all the parameters that I've looked at in the SYK model, everything's been nice and stable. But you could imagine doing more careful experiments with other Hamiltonians in SYK, and maybe you could see some instability. So that would be super interesting.
Yeah, and just another very naive question. So, when studying quasi-normal modes in the context of ADS black holes, we usually impose Dirichlet boundary conditions at the boundary. Like, I just want to know if this choice is particularly motivated by something from ADS CFT, because we can also use Robin boundary conditions there. I mean, the choice of boundary condition is not unique.
Yeah. In ADS CFT, I guess if the operator dimension is big enough, then you probably want to choose those Dirichlet boundary conditions. I mean, if you're in this weird window of order 1 delta, you can also choose alternate boundary conditions, and then it's some double trace deformation. But I think we can take the operator dimension to be order 10, and then you only have one option.
I see. Thanks.
Yeah.
Okay. Are there any other questions? Okay, I don't think there are other questions. So let's thank Matthew again for a very nice talk.
Thanks a lot.
Yeah.
Thanks, Matthew.
Take
Thanks
care,
again.
guys.
Yeah,
Yeah.
bye. Have a nice day.